Hey all, my name is Sergei. I'm founder of Embucket. Today I want to share our adventure on running DataFusion in AWS Lambdas. First, let me explain what Embucket is. And this is open source. I think I have one. Yeah, okay. So yeah, Embucket is an open source Snowflake wire-compatible lakehouse database. And we're using Apache DataFusion as our query engine and Apache Iceberg for storage. I was thinking what the joke I could tell about Apache Iceberg given the previous couple of talks, but didn't come up with any. So yeah, using Apache Iceberg, not a Lake. And Apache Iceberg is a very, very first-class citizen for us. Again, written in Rust, we target to run Snowflake workloads without any modifications. So you just need to change the connection URL, and it basically runs exactly as is. And you can run this locally on EC2, and we're running this on serverless in AWS Lambdas. We are targeting bring your own cloud model. So you basically run it yourself, you own compute, you own the data, everything. Okay, so SnowSQL, dbt, superset, they all just work. You might ask, why Lambda? Good question. Please don't ask me. But yeah, we're actually trying to be phonetically compatible with Snowflake. And we believe that it's not just API wire compatibility, it's not just SQL dialect. Snowflake is an amazing piece of software, and it's like pleasure to use, just because Snowflake has to operate and manage it for you. So we're looking for some primitives in the cloud that will allow us to be like Snowflake. And Lambdas are great here, right? So there are no clusters to manage, no servers to run, no fleet. It allows you to scale to zero. So you pay for query, you do not pay for your fleet, not per hour, and basically gives you like amazing scalability. 1,000 queries, just execute like this. The hard part is that AWS Lambda is notoriously constrained. It's arguably the most limited environment in the cloud primitives. So there are just few gigabytes of RAM. Ephemeral disk is almost non-existent. 6 megabytes of payload is allowed, and there's no persistent state to use. So we work around this with state externalization. Our tables and our namespaces are basically managed by AWS as table buckets, and it's basically managed Iceberg catalog by AWS. All the storage is managed by AWS, and it works great. We use DynamoDB to use session state metadata views, and query results right now are streamed back directly. They should not, but right now it is what it is. So we fetch all the catalog metadata on start, and the session context is built on each request. So basically, boils down to one of the previous speakers as well. So let's talk a little bit Lambda constraints. So again, not a lot of RAM, not a lot of disk, not a lot of CPU. So we have to use DataFusion built-in memory tracking tools, and it actually helps. But some operators in the DataFusion are basically very, very memory hungry. So hash join and sort basically pretty difficult to run on any scale. And disk splitting is not really helpful in this specific use case, just because, again, 10 gigabytes of the ephemeral disk is not that much. And so it's not really helpful for us. The payload size is very limited. So select star request, basically bring all AWS Lambdas to its knees. There is a way to use streaming invocations in Lambda, and I believe these give you 200 megabytes of the data, but still pretty limited. And God forbid to use your API gateway in front of it, which comes even less payload size and its own query timeout execution. Lambda has 15 minutes maximum of running the query. Gateway, I guess it's 29. But it's pretty capable. TPCH scale factor 100 actually works great, okay. Only four queries basically, well, they run pretty quickly, but they still fail just because there is not enough memory for the Lambda, and everything else is basically passing. We used all the default settings for DataFusion here, such as batch size and the target partitions. So I believe you can tweak them such that query 18 will pass, but then I believe it will fail with 15 minutes time limit. Okay, so non-functional problems alone. We also have a couple of functional problems. So Snowflake clients basically expect stateful servers. So when they talk to you, they basically send you state. They use warehouse, use database. Hey, here's my time zone. I want to use in my queries, and they send SQL one by one. And connections have to be there, and variables as well. So we have to reconstruct the whole session context on each request, such that even if we hit the new cold start, basically all the same, and it works like a single session. So yeah, we try to bring the illusion of statefulness on top of stateless substrate. I also want to touch a bit about the Snowflake interoperability. We're actually using S3 bucket, and we're using Iceberg tables. And Snowflake recently added the support for Iceberg. And with the help of AWS Glue, it's possible to point both engines to the same data. And this way, it allows Embucket to run side by side with Snowflake. So no migration required. And you basically can move workloads one by one gradually. And it actually works. So basically works that Snowflake writes and Embucket can read. And then Embucket reads and Snowflake can write. Embucket can write and the Snowflake can read. Yeah, sorry. So yeah, Apache Iceberg is an open format, and it's good in this specific use case. Let's see how that progresses here. That's the schema, how we actually work. So we're using this SnowSQL is basically some sample tooling that can talk Snowflake dialect. You specify connection bucket, you specify connection default that goes to your Snowflake account. You point Snowflake to the AWS Glue. Glue knows about S3 tables, and Bucket natively talks to S3 tables buckets. And this is how you achieve full interoperability between the two. And yeah, I guess that's it. Thank you.